Jai Shri Gurudev. My dear students, today I am going to discuss the crystal field theory of coordination complexes. This is for 2nd B.Sc, 4th semester CBCS students. My dear students, in this topic I am going to cover the following points: the features of CFT, grouping of d orbitals into T2g and Eg, crystal field splitting in octahedral complexes and tetrahedral complexes, crystal field stabilization energy, spectrochemical series, the magnetic properties of metal complexes based on CFT. Let us know about the important features of CFT. According to CFT, sentimental ion, it is at the center that are surrounded by number of ligands. Each ligand consists of one or more lone pair of electrons. According to this theory, ionic ligands are treated as point charges and neutral ligands are treated as point dipoles. The bonding between the sentimental ion and the ligands are purely electrostatic in nature. The metal ion and the ligand do not mix their orbitals. Here, the mixing of orbitals do not take place. Before going to the grouping of d orbitals, we must know about shapes of S, P, D and F orbitals. You already studied in your previous classes about the shapes of S, P, D orbitals. The shape of S orbital is spherical, P is dumbbell shape and D is double dumbbell shape, like that. The shapes of d orbital, the shape of d orbital is double dumbbell shape. This consists of 5 degenerate d orbitals that are dxy, dyz, dxz, dx square minus y square and dz square. There are 5 degenerate d orbitals that are present in d orbital. Here, the grouping of d orbitals takes place. You see here the dxy, yz and zx. In this, the lobes of orbital, they are lying in between the axes. In this type of orbitals, the lobes of orbitals, they are lying along the axis. You see in this picture, the lobes are lying along the axis. Here, lobes are lying in between the axes. Grouping of d orbital into two sets. One is T2g set and the another one is Eg set of orbitals. These are all T2g set of orbitals that are dxy, dyz, dxz orbitals. These are all called as T2g set of orbitals. In these orbitals, the lobes are lying in between the axes. You see here, the lobes are lying in between the axis. This is x-axis, this is y-axis, this one is z-axis. Here lobes are lying in between the axis. That's why T2g set of orbitals are called non-axial orbitals. T2g set of orbitals are called non-axial orbitals. The second one is Eg set of orbitals. D orbital can be split into two sets. One is T2g set and the second one is Eg sets. Here Eg set of orbital consists of these two orbitals. Those are dx square minus y square and dz square. Here the lobes of orbitals lying along the axis. Here this is x-axis, this is y-axis, this is z-axis. Here what happened, the lobes of orbitals, they are lie along the axis. Here also the lobes of d orbital, it is lying along the axis. That's why each set of orbitals are called as axial orbitals. Each set of orbitals are called axial orbitals because their lobes are lying along the axis. Okay. Crystal field splitting. You see in this figure, this is the d orbital, the free metal ion. This is d orbital in the excited state. When ligand come approaches to center metal ion, the d orbital can split into two sets. One is T2g, another one is Eg set. It is split into, d orbital is split into two levels or two sets, that are T2g and Eg. This is what we called crystal field splitting. Crystal field splitting is defined as the degenerate d orbitals split into two levels in the presence of ligands is called crystal field splitting. This is octahedral complex. Coordination number is 6, means this consists of 6 ligands. Central metal ion, it is at the center, and all the 6 ligands are occupy 6 corners of the octahedron. You see here, the central metal ion, it is at the center, and all the 6 ligands are occupy 6 corners of the octahedron. Then let us discuss about how crystal field splitting takes place in octahedral complexes. Crystal field splitting in octahedral complexes. This is the octahedral complex. The central metal ion, it is at the center, and all the 6 ligands are occupy 6 corners of the octahedron. The ligands are, when ligands come closer to central metal ion, when ligands come approaches to central metal ion, the coordinate bond is formed. The dx square minus y square and dz square orbitals lying along the axis, while dxy, dyz and dzx orbitals, they are lie in between the axis. Hence, ligand approaches to central metal ion. What happened? The dx square minus y square and dz square orbitals experiences more repulsion from the ligand field. Then their energy increases. The energy of Eg set is increases. The energy of dxy, dyz, dzx orbitals decreases because of there is a less repulsion from the ligand field. That's why their energy decreases. You see in this diagram, this is the d orbitals in the free metal ion. This is the degenerate d orbitals in the excited state. When ligand come approaches to central metal ion, what happened? The Eg set of orbitals experiences more repulsion from the ligand field. That's why their energy increases. The energy of Eg set is plus 6 dq. Then T2g set of orbitals experiences less repulsion from the minimum repulsion from the ligand field. That's why the T2g set, the energy of T2g set decreases, that is minus 4 dq. Del naught, it is nothing but it is the energy gap between T2g set and Eg set of orbitals. Del naught is the energy gap between the T2g and Eg set of orbitals. Del naught is equal to 10 dq is for octahedral complexes. This is the crystal field splitting in octahedral complexes. Crystal field stabilization energy. It is also known as CFSE. It is defined as the lowering of energy of a transition metal ion in a given ligand environment due to crystal field effects. That is what we called CFAC, crystal field stabilization energy. That can be calculated by using these formulas. By using these formulas, we can calculate CFAC for octahedral as well as tetrahedral complexes also, for both high spin and the low spin complexes. Spectrochemical series. Spectrochemical series helps us to know about whether the given ligand is strong or weak. Spectrochemical series is defined as it is a list of ligands that are arranged in the order of their field strength. That's what we called spectrochemical series. Spectrochemical series is nothing but it is a list of ligands, that's all. List of ligands that are arranged in the order of their field strength, or that can be arranged as in the increasing order of their del value. That is what we called spectrochemical series. Look here in this series. This is iodo, bromo, chloro, fluoro. These are all weak field ligands because their del value is less. Here you observe here, this is NH3, ethylene diamine, cyano, carbonyl. These are all strong field ligands because their del value is large. My dear students, you must know about the complexes consists of the weak field ligands. That complexes are called high spin complexes. Those complexes contain strong field ligands, then we call it as low spin complexes. Okay, here in the presence of strong field, there is a large energy gap between T2G and EG set of orbitals. In the presence of weak field ligands, the energy gap between T2G and EG is very less. The next question is, how can we distribute the electrons to this T2G and EG set of orbitals? How can we distribute the electrons in the presence of strong field and then the presence of weak field? How can we distribute the electrons? That is the questions. Distribution of d electrons into T2G and EG set of orbitals. It is depends upon whether the given ligand is strong or weak. By knowing the ligands are strong or weak, by knowing that, we can distribute the electron to T2G and EG set of orbitals. There are two cases. If the complex containing weak field ligand, if the complex containing strong field ligand. In the presence of a weak field ligand, the energy gap between T2G and EG is very small. In the presence of a weak field ligand, the energy gap between T2G and EG is very small. Hence, the distribution of electrons takes place according to Hund's rule. What Hund's rule tells? The Hund's rule states that the pairing of electrons takes place only after all the orbitals are off-filled. That means first we are off-filled all the orbitals, then only pairing of electrons takes place. The second case is the ligands are strong. If the complex containing strong field ligands, then the energy gap between T2G and EG is very large. due to presence of strong field ligands, the energy gap between T2G and EG is very large. Hence, the distribution of electrons is distributed to T2G first, then goes to EG set of orbitals. Up to 6 electrons that are distributed to T2G set. The 7th electron goes to EG set of orbitals. You see here in this figure, D1, D2, D3 systems are same as strong field and weak field complexes. In D5 system, for example, D5 system, in strong field ligands are present in a complex, there is a large energy gap between T2G and EG set of orbital. That's why all the 5 electron comes to T2G in case of strong field ligands. In case of weak field ligands present in a complex, the 5 electrons are fill up to all the 5 orbitals according to Hund's rule, as taken place in the D6 and D7 system also. How can we decide the given complex is high spin or low spin? That can be decided by the concept pairing energy. What is pairing energy? Pairing energy, it is the amount of energy required to pair 2 electrons in a same orbital. That is what we called pairing energy. If pairing energy is greater than del naught means crystal field splitting energy. Pairing energy is greater than crystal field splitting energy, unpairing of electrons takes place. Then high spin complexes are formed. High spin complexes consists of weak field ligands. If pairing energy is less than crystal field splitting energy, the pairing of electrons takes place and the resulting complex is low spin complex. Low spin complex consists of strong field ligands. This is the calculation of CFSE for octahedral complexes for both the high spin and low spin complexes. For D1 system, T2G consists of 1 electron. The CFSE is that can be calculated by using the formula. This one, CFSE is 4 into number of electrons in T2G set minus 6 into number of electrons in EG set of orbitals. By using this formula, we can determine CFSE for D1 to D10 systems. This is tetrahedral complex. Their coordination number is equal to 4. Means this complex consists of 4 ligands. You see in this figure, the central metal ion it is present at the center and all the 4 ligands are occupy alternate corners of the cube. You see here, this and this. The 4 ligands are occupy 4 corners, alternate corners of the cube. In this tetrahedral complex, the ligand it is lie in between the axis. You see here, this ligand it is in between x and y axis. The ligands are lie in between the axis. Here also. All the 4 ligands are lying in between the axis. In these complexes, how crystal field splitting takes place? When ligand come approaches to metal ion, what happened? dxy, yz and zx orbital experiences more repulsion from the ligand field, hence their energy increases. Then x square minus y square and dz square orbitals experiences minimum repulsion from the ligand environment, hence their energy decreases. In this figure, this is the d orbital of free ion. This is the orbital in the excited state. When ligand approaches to centrometal ion, what happened? Dxy, yz and xz orbitals experiences more repulsion from the ligand field, hence their energy increases. These orbitals dx square minus y square and dz square orbitals experiences less repulsion from the ligand field, hence the energy of E is decreases. In this way, crystal field splitting takes place in tetrahedral complexes. You observe in this figure, this is the comparison between the crystal field splitting in octahedral complexes and tetrahedral complexes. This is the degenerate d orbital. This is d orbital splitting in octahedral complexes. This is d orbital splitting in tetrahedral complexes. By knowing this, we conclude that the d orbital splitting in tetrahedral complexes, it is exactly reverse of d orbital splitting in octahedral complexes. Let us discuss about the magnetic properties of metal complexes based on CFT. The first complex is this one, hexamine cobalt 3 plus ion. Hexamine cobalt 3 plus ion. NH3 is a neutral ligand, their charge is 0. This 3 plus is the charge of complex ion. Then oxidation state of cobalt is 3 plus. The atomic number of cobalt is 27. The electronic configuration of cobalt is argon 3d7 4s2. The electronic configuration of CO3 plus ion is argon 3d6. NH3 is a strong field ligand. NH3 is a strong field ligand. That's why the splitting of d orbitals into T2g and Eg is very large. That's why there is a large energy gap between T2g and Eg set of orbitals. That's why here d orbital consists of 6 electrons. All the 6 electrons comes to T2g set only. Here in this complex, it doesn't containing unpaired electron. Hence, the complex is diamagnetic in nature. This is the magnetic properties of this complex. Dear student, please note this. If the complex containing unpaired electron, then they exhibit paramagnetic property. If the complex doesn't containing unpaired electron, then they exhibit diamagnetic property. The second complex is hexafluorocobaltate 3 plus. Hexafluorocobaltate 3 plus ion. In this ion, the charge of complex ion is 3 minus. The charge of ligand F minus, that is there are 6 ligands are there. There are 6 minus. That's why the oxidation state of cobalt is 3 plus. The atomic number of cobalt is 27. Electronic configuration is this. Electronic configuration of CO3 plus is argon 3d6. Fluoro is a weak field ligand. This is known by spectrochemical series. F minus is a weak field ligand. That's why there is an energy gap between T2g and Eg set of orbitals is very small. The energy gap between T2g and Eg set of orbitals, it is very small because it is a weak ligand. That's why the distribution of electrons takes place according to Hund's rule. Here D consists of 6 electrons. The 6 electrons are distributed according to Hund's rule. Here in this complex, there are 4 unpaired electrons are present. Here there are 4 unpaired electrons are present, hence this complex is paramagnetic in nature. This is a third complex, hexacyanoferrate 2 plus ion. This is the name of this complex, hexacyanoferrate 2 plus ion. Here this is cyanide, it is a strong ligand. 4 minus is the charge of this complex ion. Cn minus, there are 6 ligands are there. This is 6 minus, this is 4 minus, hence oxidation state of iron is 2 plus because the complex is electrically neutral. Here the atomic number of iron is 26. This is the electronic configuration of iron, and this is the electronic configuration of Fe2 plus. Fe2 plus is argon 3d6 4s0. Cn, it is a strong field ligand. Cn minus is a strong field ligand. Cyano, it is a strong field ligand. As a result, the d orbital can split into T2g and Eg is very large. There is a large energy gap between T2g and Eg set of orbitals. That's why the distribution of electrons is to T2g only. Here D consists of 6 electrons. That's why all the 6 electrons are comes to T2g set only. Here it isn't containing unpaired electrons. It isn't containing unpaired electrons, hence this complex is diamagnetic in nature. It isn't containing unpaired electrons, hence it is diamagnetic in nature. This is the fourth complex, hexacyanoferrate 3 plus. Hexacyanoferrate 3 plus. Cyano, it is a strong ligand. Its charge is minus. 3 minus is the charge of complex ion, and the Cn minus, there are 6 ligands are there. This is 6 minus, and the oxidation state of iron is 3 plus here. This is the atomic number of iron 26. Electronic configuration of iron is argon 3d6 4s2. Electronic configuration of Fe3 plus is argon 3d5 4s0. We know that cyano is a strong ligand. It is a strong ligand. Due to presence of strong ligand, there is a large energy gap between T2g and Eg set of orbital. Here, due to presence of cyano ligand, there is a large energy gap between T2g and Eg set of orbitals. Here, d orbital consists of 5 electrons, hence all the 5 electrons are comes to T2g set only. All the 5 electrons are comes to T2g set only. Here in this orbital, this is one unpaired electron is present, hence this complex is paramagnetic in nature. This is a paramagnetic complex because it consists of one unpaired electron. This is about the chapter crystal field theory. Thank you.